Previsualization has always been the bridge between a creative idea and final production. In film, game development, and architectural design, creators spend weeks or months iterating on scene layout, object placement, camera motion, and spatial temporal dynamics. But when we hand this workflow over to modern generative AI, we run into a fundamental bottleneck. Current models treat previsualization as a one-shot synthesis problem. You feed a prompt, you get a video or image back, and that's it. There's no persistent state. You can't easily tweak a single object's pose, expand the environment without regenerating everything, or plan a camera move that actually respects the scene's 3D geometry. The result is spatio-temporal inconsistency, identity drift, and weak controllability. What's missing is an explicit, editable, and persistent working representation. That's exactly what StateFlow solves. Instead of generating isolated frames or videos, StateFlow models previsualization as the continuous construction, evolution, and access of a structured 3D world state. Let's look at the core formulation. StateFlow formalizes previsualization as a state-based process. Given an input condition, the system first builds an initial world state. Then it updates that state over time. Finally, it produces observations through a controllable access function. This explicitly separates the world state itself from its evolution and its rendered output. In traditional generative pipelines, these are tangled together. In StateFlow, the world state is object-centric. At any given time, the world is just a collection of objects, where each object is defined by three core components: its geometry, its spatial pose, and its semantic attributes. Remove any one of these, and you lose either visual realization, spatial consistency, or controllable evolution. This structured representation is what makes iterative editing and long-horizon planning actually possible. The first stage is state construction. The goal is to translate a natural language prompt into a coherent 3D scene. The challenge here is that a single view can't reliably capture both fine-grained object appearance and global spatial layout. StateFlow solves this with a prior-guided, conflict-aware dual-view initialization. It generates two complementary references: a front-view image for object identity and local geometry, and a bird's-eye view for ground plane placement and scene topology. Because these are generated independently, they inevitably disagree on object counts, spatial placement, and appearance. StateFlow doesn't just merge them blindly. It factorizes the cues and assigns asymmetric roles. The front view acts as the appearance source. The BEV acts as the spatial source. When counts mismatch, a vision language model evaluates the context. Objects that are physically unsupported or contradict the prompt are down-weighted as hallucinations. Plausible elements are retained. Then each object is lifted into 3D using a grounding-aware operator that places grounded objects on the surface and infers height for floating ones. Finally, the system runs a lightweight, training-free optimization that balances front-view appearance, BEV layout, VLM grounding priors, and physical constraints like collision avoidance. The output is a spatially structured, physically plausible 3D world that's ready for iteration. Once the world is built, we need to change it. This is where state evolution comes in. Traditional approaches handle edits by regenerating video or rerunning the entire generation pipeline. StateFlow takes a completely different route: intent-guided structured state transition. Instead of asking a diffusion model to implicitly hallucinate every dynamic process, the system queries the structured state table and generates a compact transition plan. This plan specifies exactly which objects or scene attributes to update, the type of transition, and the target state. At the scene level, you can expand the environment by instantiating new regions and merging them into the existing layout, or change the style by rewriting semantic descriptors without touching the underlying geometry. At the object level, you can update poses for character animation, apply rigid motion for vehicles, or handle complex events like explosions through asset substitution. When a continuous simulation isn't feasible, StateFlow swaps the geometry term for a target state asset while preserving the object's identity and semantic role. The result is a world that evolves explicitly, remembers its history, and remains fully editable. The final stage is state access, which handles how we interact with the world for downstream tasks. Camera planning is the primary interface here. Previous text-only camera generation methods rely heavily on linguistic intent and completely ignore geometric reality. StateFlow fixes this with a two-system design: world state camera planning with render feedback reflection. First, a vision language model proposes an initial camera trajectory based on director intent and shot style. But it doesn't stop there. The system executes that proposal in the 3D world through low-cost rendering and evaluates the output. It checks for intent mismatch, target invisibility, poor framing, occlusion, and collision risks. Then, a reflection module converts those discrepancies into local repair candidates. Visibility issues get adjusted by changing camera distance or field of view. Occlusion and collision risks get resolved by shifting the viewpoint height or azimuth. The system searches only over these issue-driven repairs, selects the best trajectory, and iterates until the shot is geometrically and narratively sound. This is entirely training-free and requires no camera trajectory annotations. It just uses rendered feedback to ground semantic intent in physical reality. This architecture naturally supports two major previsualization workflows: cinematic video creation and 3D game prototyping. For video, it handles storyboarding, shot planning, and production by reusing the same persistent world across different camera angles and time steps. For game prototyping, it enables interactive content design where creators can test spatial layouts, object interactions, and player viewpoints in real time. The results back this up. On standard benchmarks like VBench, StateFlow outperforms leading video generation and agentic methods in subject consistency, background consistency, motion smoothness, and flicker reduction. In scene generation, it beats baselines like Sin City, SAM 3D, and PartCrafter in clip alignment and spatial coherence. User studies and MLLM evaluations consistently show higher scores in layout plausibility, identity preservation, and previsualization usefulness. Most importantly, ablation studies confirm that every component matters. Removing the BEV layout breaks global structure. Skipping conflict resolution creates duplicated or missing objects. And relying on VLM-only camera planning leads to framing failures and collision artifacts. The render feedback loop isn't just a polish, it's a necessity. StateFlow represents a fundamental shift in how we approach generative previsualization. We're moving away from treating AI as a one-shot image or video synthesizer, and toward treating it as a world-building engine. By maintaining an explicit, persistent 3D state, creators can iterate on geometry, evolve narratives through structured updates, and plan cameras that actually respect the scene's physical layout. The framework is currently limited by the inference speed of its underlying third-party models, so fully real-time interaction isn't there yet. But the architecture itself is training-free, model-agnostic, and designed to plug into whatever generative backbone advances next. If you're working in film, game development, or architectural design, this state-centric approach is exactly the kind of intermediate representation that bridges the gap between raw generative capability and production-ready workflows. I'll leave the paper and project page linked in the description if you want to dig into the math, the ablation studies, and the full pipeline diagrams. Let me know in the comments how you think explicit world states will change the creative pipeline, and I'll see you in the next one.